Hello. So before we get to the next topic, okay, let me briefly readdress what's covered here about this aliasing of this 399 hertz. Okay, so we observed. So here, you can see my sampling rate is 8,000, and now let me generate a tune of 399 hertz. Okay, so you can see this is of this beating pattern. Yeah, kind of beating pattern. It's not really like the real 399 hertz. So if I increase the sampling rate to a little bit, not to like over 10,000, let me generate the same tune of 399 hertz. It's like this. Okay, so let me play this one. Okay, so this is 399 hertz, but for this is the same tune, but it's generated under a much lower sampling rate. It doesn't really produce any sound on my computer. So comparing these two waveforms, you can see actually this is not a pure sine tone at all, right? There's some beating, some amplitude modulation effects there. So in this video, the author like explained why it happens, right? Because it said at the half of sampling rate, which is 4,000 hertz, it's not a clean cut. Okay, it's not clean cut. There's some ramp, some buffer here, so that it actually still allows some of these frequencies here, right, to be fold over. So if you recall the folding over, so this is the 399 hertz, right? So any frequency here will be fold over, okay, will be fold over as 399, and all those frequencies here, once it's fold over, it will be create this beating pattern with this. Okay, so what is beating? So beating, okay,
there to be.
what is beating? So here is the formula. Okay, beating is just the sum of two sinusoids, but the effect happens because these two frequencies are too close to each other. Okay, if the two frequencies of like 300, 500, there will be no kind of beating pattern. When two sinusoids adding together, if you recall this trigonometrical formula, it will be the multiplication of two cosine waves, and when the two frequencies are too close to each other, right? Then a minus b is 2, like then this cosine is of only 1 hertz. This is 1 hertz cosine, and this is some cosine of a plus b minus 2 is like 400 hertz. Therefore, you are using a kind of 1 hertz tone. 1 hertz, right? 1 hertz is once per second. 1 cycle per second. When you multiply this very slowing varying tone. So this is a very slowing varying tone. When you multiply this to this tune is like much quicker, right? So when you multiply these two together, you will get something like this. So this is the beating. There are multiple ways to visualize or to produce this effect. Actually, also, right? In the video, it shows the author shows like how you do this in Audacity, and we can also do this using pure data. Okay, so first, let me show you how to create beating pattern using Audacity. So actually, it's pretty easy. let's see, let's follow the instruction here, okay? Let's produce two tone of 400 hertz and 402 hertz. So here I'm creating a track of standard sampling rate. So now I'm not playing with sampling rate, so I just use what's default. And the tune I choose is 400 hertz. Because we are adding two tones together, it's better not to have amplitude too high. Maybe 0.4, and the duration can be shorter. Let me generate. Okay. So maybe let me delete those two. Okay, so okay, let me play this. Okay, so this is a 400 400 hertz. Rename track to 400 hertz. Okay. So let me now let me add a new track. Okay. And let me produce a 40 hertz tune here. So it's of the same sampling rate. Okay, standard sampling rate generates tune of 402 hertz. Generate. So you can see these two waves are actually very close to each other. The wave, the period, the waveform. Let me zoom in. Okay, because they're actually pretty close to each other. The difference is only 2 hertz, right? For 400 and 402 hertz. So this is just a little bit quicker than this one. Okay, so they're very close to each other. So how to add these two tracks together? So in Audacity, there is a function called mix. Okay, so now you select these two tracks like this, and you go to tracks, mix and render to new track. Okay, so you're actually mixing these two tracks together. So now, actually, you can see, right? This is creating something like this beating pattern here. So let me play this. Okay. This is not that obvious because yeah, the duration is too short. Okay, let me redo everything, make this longer. Okay, just to make this longer. So let me choose still 2.2 seconds. Generate tune. $400. Here this. Yeah, let's go to tracks, mix and render to new track. Okay, so you can see this is a beating pattern. And let me play this. Right. $400. 402. There's summing them together. Okay, so this is what the beating like sounds like. Okay, so this is a basic kind of audio or sound property, and it's always used to tune the musical instruments, you know. So when you have two sine tunes very close to each other, like you want to tune a musical instrument like, let's say 400 hertz, but if you use your ear, listen to 400 or 402 hertz, they're actually pretty close to each other. I mean, at least me, I cannot distinguish these two tunes. So let me play them again. in this one, right? So they're pretty close to each other. How do you distinguish 400 between 402 or 401 so 401 hertz? So what they do is that you will have a standard 400 hertz tune, and you just use that tune to approach, right, your musical instrument. And when the two tunes are pretty close to each other, but there is a little difference, they will create this pattern. Okay. So you will hear this pattern and you know these two tunes are close to each other, but they are different. So until you tune the two the two sound waves to the same pitch. Okay. If it's two 400 hertz tune adding together, there will be no beating. Okay. So maybe let me do this. So now let's say this is our standard tune, and this is our musical instrument. But now our musical instrument is tuned to perfect 400. And now if I mix and render those two tracks together, right? So this is the new track I get. Let me play this track. Right? So when you add two tunes of the same pitch, there will be no beating. But if there is small difference between them, it will create this beating pattern. And also, you can say, what if, like, I have 400, but what if another tune is like 500, right? So their difference is actually much larger than 1 or 2 hertz. What will happen? Okay, we can try this out, like 500. Okay, let's mix and render them. So this is the generated tune. Okay. Right? Let me zoom in. You can see this pattern here. So this is actually 400 plus 500. Okay, so 400 hertz plus 500 hertz. Right? So you can see this beating is still here. It's somehow you can see this beating, but this is much quicker. Okay, so that you cannot perceive this kind of rhythmic beating pattern because it's already became pitch. Okay, because this is too quick. The frequency is too quick. But this kind of package, this shape is preserved. And when you listen to this track, if you have this trained ear, I think you can just distinguish, okay, there are two tunes, 400 and 500. So what we can do, to visualize this tune is actually realize the frequency. You go to tools. No, I analyze. Okay, analyze plot spectrum. Interesting. It should be this one. Okay, let me probably plot here. Spectrogram. Okay. So actually you can view the waveform this is wave format. This is spectrogram. A spectrogram is actually a heat map. So the X is still time. The Y is frequency here. Okay, this is frequency. So you can see this frequency, it's actually 400 and 500. Okay. Okay, so you can see there are actually two lines here. One is 400, one is 500, because we have two sinusoids adding up together. So you can visualize from here. Okay. So what I really want to do is to analyze this plot spectrum, but I don't know why there are many frequencies presented. Oh. Yeah. Yeah, this is a little bit weird because I'm expecting actually you only have two sinusoids. Okay. Let me do this. Maybe let me delete everything and then analyze the spatial one. Yeah, this is weird. Probably I'm not very sure how they create this graph, but there should only be like two sinusoids here, right? Maybe add a new track and generate a pure tone again. 500 and go to analyze plot spectrum. No, this is wrong, right? I think there's some new. Yeah, but in this video, if you remember what we just watched, the video when the author kind of plots this spectrogram, there was only one line. But I don't know why it's not showing on my computer. Here, right? Because when this author generates a pure tone and this give you like 1 hertz or one frequency. Yeah, this is weird, but this is just some a glitch or some bug. Yeah, probably yeah, there's some settings wrong, but usually it won't happen. Okay, it shouldn't be like this. I think yeah, maybe it's better to view this spectrogram. You can see it here is only one frequency, right? At 500 because it's pure tone, and here if you view its spectrogram, there are two lines, okay? Because there are two sine tones adding together, 400 and 500 adding together. Okay, whatever. Just some weird thing. Okay, so now I think I'm going to introduce you with pure data. Yeah, I'm trying to introduce you with pure data, and I don't think we will finish this Audacity today. So we'll continue next week for our next lecture on Monday, and then your assignment 4 is due like next Sunday. So you still have enough time, to do the assignment. Because the function of these two softwares are pretty similar, but you can, if I do this comparative, teaching, then you will kind of say like what's the advantage and disadvantage of these two softwares. So, okay, don't do this. Let me go to PD. Let me do everything from scratch. Okay, so here is something that's called DSP. You need to check this DSP here to make sound. Okay, you need to check this box so that the program will make sound. It means sounds on. So you go to File, New, then it gives you a new canvas. And so first, what I want to do is I want to make sound. I want to make a pure tone, okay? Like what we just did in Audacity. I want to make a pure tone and I want to hear that pure tone. What I will do is that if you go to put, there is object. So on this keyboard is Control-1, okay? So you either use Control-1 or you just put. So I'm going to use my mouse because you cannot see my keyboard, okay? But for you, it's just easier to use Control-1 to create an object. Whatever. In PD, what is a sine tone? I think you can use sine. There should be sine. No, maybe this one. Okay. Okay, whatever. But usually we use this OSC. Okay, this object. So OSC, if you right click this object and go to help, it gives you an introduction. What is this object? And if you use this control plus, okay, you can just zoom in this interface. So OSC is a cosine wave oscillator. Okay, so OSC is oscillator and it produces a cosine wave. Okay, so we know OSC is an object that can produce sine tone. I mean pure tone. Okay, sine or cosine, it doesn't matter. It's a pure tone. But how to make sound? There is an object. Let me put an object. It's called DAC. Okay, DAC is digital to audio converter, which means what comes out of this is the digital audio, and you want to convert this through the speaker, and then you can hear the sound. So the tuta here, it means this is a signal. Okay, it's an audio signal. Tuta means audio signal. But whatever, this is the easiest thing we are creating here. So once you have this oscillator, you want to have some number box. Okay, then you put a number box here, and then it gives you a number. And if you link this number to this oscillator, it inputs the frequency. Okay. Okay. So this is comment. If you put a comment here, it's control 5. Okay. Let me give some comment. This is a frequency. So you input some frequency. Let's say I want for 0 Hertz, and then you can just link this to DAC, right? Then you can hear the sound. It's 400, and if you check this is edit mode. Control E. If you type Control E, you will go there and you can slide this frequency. Right? If it's below 20 Hertz, you cannot hear this because it's beyond your perception. If it's above, I still cannot hear this. Here I can hear this. Right. Let me stop this. So there are 2 modes. Edit mode. Okay, if you go to edit, this edit mode and not edit mode. So in edit mode, I can just create object and just change these objects. But in non-edit mode, I'm just doing this operation and play those sounds. So this is a very, very easy sound producing object. Only 3 sound producing system, only 3 objects. But now I want to switch. Because so far I cannot switch on and off. If I want to switch off, I have to delete this link, right? This is not that convenient. So what I want to do, I can put a toggle. Okay, Shift Control T is a toggle, so it's actually a switch, like on and off. What I will do, I will add another object. Put object is it's time. Okay. So I will multiply this oscillator, this cosine wave, and this toggle, and then I can output this sound. Okay. So now let me exit this edit mode. Right? Maybe this is too loud. Let me. So you can see there are two what's the name? Nodes, two nodes of this deck. Actually, it means like left and right. Okay, this is stereo. This is left ear, right ear. So if I don't link this one, if you now hear this sound using your headphone, you should only be able to hear the sound from your left ear. So your right ear will be silenced, right? Only from the left channel. So usually, if you do this to two channel, you can hear from your both ears. Okay, so this is easy, like on-off kind of device. So the first experiment I want to do here is the fold over. Again, it's about aliasing. It's this graph, right? Is this graph aliasing? So now I want to hear the aliasing in pure data. What I would do is that, okay, so first let me introduce you with this. Okay, if you go to media, there is audio settings. Okay, so you can see here is the sampling rate is 44100. Okay, the standard sampling rate, and there's some delay and the quantization. Okay, we will talk about quantization later on. Not really now. So we will use this standard sampling rate. Okay, we won't change the sampling rate, but I'm just showing you where you can check it, and if you want to, you can just change it to yeah, another number. We will leave it as the default. So we know the fs is 44100 hertz now. So what we can do to experiment with the Nyquist limit is that, let me go to edit mode. Okay. Delete this line, put this there. So now I want to give a ramp. Okay, let me put object. Actually, it's called line. Okay, so go to help. So line is actually a ramp. So what a line does is that it just gives you a line. If you think about this, right? Just gives you a line like this. So you can specify the start and end point, and it just gives you a line from the start to end. So what we will do here is that I will put, this is control 2, okay, a message, control 2 and 0. So I won't set my start point as 0. Okay, so this is 0. Let me link it to the line. And let me create another message for line, which is 44100. Okay, so this is our fs. And then you can specify the time, like how long it takes from 0 to 44100. Okay. So we know this is our fs. Okay. This is our fs. So based on our this Nyquist limit, this graph would be like this, right? It will fold over. So for now, I'm generating a line here from 0 to 44100, and I want the system to go from 0 to 44100 using maybe 8 seconds. Okay, so this is the, okay, if you go to help, you can just, it will tell you like how much time it takes from this point to that point. So this is 8 seconds. So let me link this to here. and link the line to my oscillator. Okay, and exit edit mode. Okay, let me turn on this and let's listen. Right? So it goes back. So if it's not a computer, if I create a line like go from why it doesn't work? Okay, if I create a line from 0 to 44100 in real life, what we will hear is that the sound actually goes from 0 to almost like 20, right? 20,000. And then all the sound above 20,000, we won't be able to hear this. So the sound will somehow end at this highest frequency we can hear. But because this is computer and because of this fold over, right? So now when it hits this half of fs, it actually fold over. Therefore, you can hear this pitch, right? This pitch, it actually ramps up from low to high, and then it ramps down from high to low. And this is the auditory effect of this fold over here. Okay, let me play this again. Yes, so I temporarily take assignment 3 down because I want to make it a discussion. Yes, but the homework will be the same. It will be the same content. Yeah, but I want to make a discussion so that you can see other people's response, so that you can know what other people are thinking about on this topic. Okay. So it will be up like after our lecture. Okay. Okay. So let me play this again, okay, so that you can hear this pitch ramping up and down, like folding over. Okay. Okay. Yeah, I hope it's clear. But it seems quite easy in pure data to do this. But what if you want to do this in Audacity? So there is also a way to do this in Audacity. It's not that convenient, but you can do this. What you will do is that we'll create a track, add new mono track here. We won't change the setting here. We'll leave it as default. But what we can do is we can go to the tools, and there's something called Nyquist prompt. And here you can type in this command line. Okay, you see return HZOSC. It's the Hertz oscillator, and this is ramp. So ramp is the same as the line here. Okay, the ramp and the line is of the same function. It simply provides you, from the start to end. It's just a linear interpolation. Okay. So you just type in this ramp, and this 5 is the time. Okay. So here I use 5 seconds. So here it's used 8,000 because the sampling rate is 8,000. Because now I'm using 44100. Let me change it to 44100. And yeah, I want this to be maybe 8 seconds. So ramp 8 times your fs, right? And let me apply this. Okay. So you can visualize this waveform. Let me play this. Compare it to PD. Well, it's just sim effects. Okay, sim effects. So this is how you do this ramp in Audacity. It takes some time and some knowledge, to know this, to do this some prompt, which means actually that Audacity is a much easier, like you can see, user-friendly software, doesn't require any programming knowledge. So pure data requires a little bit more programming, and it can achieve more functions. But there is also a limit of pure data. If you want to achieve like more complicated function, it's very difficult. I mean, you can do this in PD, but it will take you a lot of effort. So then you will maybe choose Python or MATLAB to achieve what you want to realize. Okay. So whatever, this is how you do the ramp in Audacity, and just hear this Nyquist limit and fold over and aliasing effect. Okay. If you zoom in, you can see more visualize. Oh, this is so dense. Okay. Yeah, of this sampling. But comparing this interface, actually, I would say Audacity definitely provides you a more user-friendly interface, and you can zoom in out very easily and visualize the waveforms, much faster, and edit directly on the audio. So this is called an audio editing software, right? But PD is called a graph user interface, GUI kind of software. Whatever. Okay. So I hope this is clear. And about aliasing and Nyquist limit, we will stop here. Okay. I'm not going to talk more about this. What else? Okay. So we just talked about beating, right? We talked about beating, and we did beating in Audacity already, just adding two sinusoids together. We can also do this easily in PD. Okay. How to do this? We know this is cosine oscillator. Okay, we just use Control D. Just duplicate this twice. And now, let's say we have, so now I'm using this Control 2, okay? I'm using this shortcut on those things. So Control 2 is a message. So again, we want this maybe 400 Hertz, okay? So this is the 400 Hertz oscillator. And here I want to use a number box, okay? Just some random number I can slide with. And now let me put an object. I want to add these two together, right? So I use add tutor. I'm adding these two cosine waves together. Okay, so two cosine waves together, and I'm using this same output device. Okay, make the sound. Okay. So again, okay, these two numbers are frequencies. Okay. So let me turn this on. Okay, I forgot to do this. Okay. So first let me make the two frequencies the same as each other. Okay. There's no difference. You just hear 1, 2. Now let me increase it. I can hear this slow beating. The beating is quicker. two frequencies, when the difference is too large, the beating kind of, the rhythm is changed to pitch. Therefore, you cannot perceive the beating as a rhythmic entity. It becomes a pitch. Okay. So now you can perceive this beating, but we can also actually visualize this as shown here. Okay, as shown in the graph. We can visualize this waveform. How to do this? Actually, we will put an array. Okay, array is just some graph. So we can name this array as beating. Probably we can make this size as maybe 44100. Yeah, it's the same as our sampling rate. Okay. So go to edit mode. Go to edit mode. We can edit this. This is a graph. How to draw to this graph? So there is another object called typewrite. Typewrite tutor. Okay. So typewrite tutor. Then where is BT? So you typewrite to BT. So this is the summation of the wave. Okay, so you will link this wave to here, and then you can write this waveform to this graph, right? And I will put a band. Okay, Shift Control B is put a band here. So I will start plot. Okay. This is too large because I'm adding 2 and I'm not really dividing this. So what I will do is that, okay, let me change this a little bit. So I will divide theta 2, which means I want to divide this amplitude to half. So it will fit into the -1 to 1 range. Okay. Here, no, let me link this new wave to typewrite. Okay, so now it's fit to -1 to 1. And again, let me put it to 400. But you can see when I type in the number here, it doesn't change because I didn't ban it. I have to manually ban this, then you can see these changes. Therefore, in order to do this automatically, I will link this to the ban so that once I change the number here, it will automatically ban this, and this will just start, drawing on the graph. So you can see now this is just some pure tone. Now let me increase this. Right? So this is beating. If it's 4.1 or 401, it's difficult to, okay, so 401 is only one peg. What's the name of this peg, right? Probably only one this kind of shape. It's 2, there's 2. The increase is 3. There's 3 of these. With 4, there's 4. Like with 5, right? Larger, so it will be so this periodic pattern will just generate like more and more, like with higher frequency, quicker and quicker. And when I increase this, a lot more. Yeah, it's still there. Let me listen to this. Okay. So this like kind of 16th per second. Right, 16th per second. Let me do this. 24 per second, 25. Now you already see, the beating pattern somehow disappeared. And if you listen to this sound, yeah, there's already like no like obvious beating there. Okay, so you can listen to the sound and you can also visualize this graph like in real time. Yeah, so this is pure data. It's easy to use and comparatively easy. And I mean, it's developed for like musicians, okay, for music programmers. Therefore, everything is like much easier and more like obvious, and it's very useful for you to do some easy experiment here, like beating, etc. Okay, so let's continue with our topics. Okay, continue with our topics. What I want to talk about now is square waves, okay? Other harmonic waves. So we always talk about sine, but we always talk about sine, like people will just wonder like why we always take this sine wave, right? There are also other types of waves like square wave, other shapes like triangle, sawtooth, and other like irregular shapes. So they are also like periodic waves oscillating all the time. It's just of different shapes. How do we represent these waves, or how do we create those waves on computer, and how do we analyze these waves by decomposing them into these sinusoidal components? Okay. So actually, people actually use this something called additive synthesis. Okay, additive synthesis to add those harmonics means the sinusoidal waves. Okay, the sinusoidal harmonics together to create the square, triangle, and the sawtooth wave. This additive synthesis, or this kind of adding sinusoids together to approximate some type of wave, is the basic of Fourier transform. Okay, it's a basic thought of Fourier transform. Especially, it's actually adding infinite harmonics. So let me go to this link. Okay, so here in this link you can see some general information about square wave. Okay, so this is a Fourier series for square wave. So you're adding those sine waves, okay, sinusoidal components infinitely from 1 to infinity, and you're adding this infinite sum of sine waves, and then you can replicate the square wave. Right. So you can also change here. So sine, okay, sine is different. So for different types of waves, it has different formulas. So this is for square wave. This formula is for square wave. What about triangle? So for triangle wave, it follows another types of formula Fourier series, right? So now it becomes square. and it's still sine, but the coefficient is different. What about sawtooth? Yeah, it's another formula here. So kind of square, triangle, and sawtooth waves are actually some standard waveforms other than sinusoidal waves, especially in the sound synthesis, right? Sound synthesis and many other applications. People will sometimes people prefer triangle wave, some people prefer sawtooth, some application prefer square wave. That's why these techniques were like developed at the first stage. Okay. So kind of pulse wave. So in your homework, so probably let me pull up your homework. Let me address some of those points. Yeah, to assist you to do the homework. So here, I want you to do some experiments using audacity. But if you use pure data, you can also do the same thing. Okay, I think if you use pure data, those things are probably will be easier, at least some of the tasks. So the first we already did, right, in our first lecture, create tracks with different sampling rates and compare the sample waves. We already did this one. Observe aliasing using generated pure tone. We already did the aliasing. Produce a beating pattern by mixing two tracks. Yeah, I already covered this part. And compare the generated square waves with and without aliasing. So this is what I want to talk about now. And this record a piece, we will cover it in our next lecture. Okay. So for these generated waves in Audacity, actually it's here. Okay, let me add new track, and you go to generate. So generate tune. This is what we use, like for this entire lecture, right? We only use this one function. So if you go to this waveform, you can see it's not only sine. You can choose other types of waves, right? Square, sawtooth, and triangle, right? And like, let me see, we choose sawtooth, 500, maybe 0.6. Let me generate. Okay. So let me zoom in. You can see this is a sawtooth wave, okay, of this shape, sawtooth shape. Zoom in better, right? Because yeah, this is a linear ramp from minus 0.5 to 0.5 because our amplitude is 0.5, okay, and then it drops to yeah, from positive to negative, and then it starts ramp up. This is the shape of sawtooth wave. Let me listen to this. Okay. Okay. So let me see. Let me rename this track as sawtooth. Let me add a new track. And let's still generate a pure tone first. Okay, it's 500 hertz. Okay, 0.4, it's not 0.5. Maybe let me change this to 0.5. Okay. Sorry, let me redo everything. Change the name to sine. Okay. Generate tune. 500 hertz, 0.5 amplitude, duration is 0.6 seconds. Okay. And let's listen. Okay, pure tone. Add a new track. Rename it as maybe sawtooth. Generate tune. use sawtooth wave. Yeah, other parameters are the same. We generate. Okay, and listen. So it produces something like much brighter. It's brighter because it contains the higher frequencies. Okay, the higher frequencies other than this 500. Okay, the upper harmonics. Maybe add a new track, and let's see triangle. Generate a tune. Let's choose triangle here. Okay, so listen to triangle wave. Okay. Finally, like we can generate. Okay, track new. Let's name it as square. Generate square wave. So you can see the square wave. We will zoom in later on. It's much brighter. It's much like there are some artifacts there. But let's don't talk about this now. But let me zoom in. Okay. So after I zoom in, you can see, right, different shapes. So this is sine wave, this is sawtooth, this triangle of this triangle shape, and this is square wave, okay, the pulse wave. Maybe let me okay, zoom in more, you can see the sampling, the discrete points. So sawtooth is ramp up, triangle is like this, right? It's like square wave is very strict square like this. So this is how Audacity generates different types of harmonic waves. Okay, listen to them again. Sawtooth, triangle, square. So what I want you to do in your homework, actually, because this square, if you go to this generated tool, you will Spotify that, except for all those types, there's another type called square no alias, right? So now let me maybe create a new track. And let me generate this tune of no alias. Okay, generate. Let me play this one. Can you hear the difference? Right? This is much more harmonic. There are some like more like artifacts and something dissonant, right? I mean, I don't know if you can perceive this. So now let me zoom in. Okay. So after I zoom in, you should see that for this square, it seems to be the perfect square here, right? But here it's much like rugged square. Okay, if you observing those points, you can see here in this square, yeah, it's these boundaries. There's some like ramp, something, some buffer here, right? Gradually changing, but here it is strict from positive, negative, positive, negative. So this is actually relation to the upper harmonics, right? When we talk about aliasing, because in this square wave, it presents too many upper harmonics, and because of aliasing, it fold over and it's added to the original sound, which makes this sound, you know, some aliasing effects, which makes this square wave sound less harmonic. But here, no aliasing, because it means it cuts off all the upper harmonics above our sampling rate. Therefore, it sounds like better. So this is the basic point. I will readdress this in the start of our next lecture and make sure you understand, you know, those different waves more, and we will also experiment it with pure data. But the idea here is it's just this, okay? It's just a kind of effect of aliasing and the fold over of upper harmonics, and which causes the square waves sounds different. Okay, let me play this again. This is with aliasing. This is without aliasing. So the second one sounds like much pleasant. Okay. So I will provide more probably provide some more resources like the videos here, and then you can watch the video, and you know, I mean, some YouTuber may explain better than me, so whatever. And I will also release assignment 3 very soon. Okay, so this is the lecture for today. Thanks for coming, and we will continue with this practical lecture on Monday next week, and then you can do your homework smoothly. Okay, so thanks for coming. Thank you. Bye-bye.
Thank you.
Thank you.